Manitoba Pulse and Soybean, like other grower groups, we do try and pay attention to the things that farmers really need knowledge in. And there's no one place to get it all. You have to spread your thoughts, your relationships, and your money really not just across the province, but across the country, across the continent, and increasingly across the world. We're fortunate that right here in Manitoba, we've got some good organizations that are listening to what we're saying about farmer needs in terms of research. And so we thought we'd get a panel together that each work on a different aspect of soil health. And we're just going to, each one of them is going to go through just a few slides and make some comments about their perspective on soil health. And then we're going to go into some questions and answers from that. So first of all, I'd just like to introduce the folks. So on my right is Dr. Matthew Bakker. He's an assistant professor in the Department of Microbiology at the University of Manitoba. He teaches and runs a research program that investigates soil microbiology, as well as Fusarium head blight disease of wheat and barley. He's a part of a large new research project that's studying the influence of soil bacteria on crop root traits. I think you can make the connection there from what Shama was saying. Prior to joining the U of M, Dr. Bakker was a research scientist at the United States Department of Agriculture, so he's got that U.S. experience. In the middle is Dr. Stephen Crittenden. He's been a research scientist in soil health and nutrient management at Agriculture and Agri-Food Canada, just down the road here in Brandon, since 2017. His research aims to improve productivity while ensuring long-term environmental sustainability of agriculture systems through soil health and soil fertility management. Stephen's research currently focuses on improving soil health and its resilience versus ecosystem trade-offs, as we talked about in our opening comments. Soil health in a changing climate and soil infrared spectroscopy. There's a great term there. And finally, next to me is Charley Sprenger. She's an ag research engineer at Prairie Ag Machinery Institute in Manitoba, or PAMI. She leads various projects involving the agronomics and logistics of farm production activities to provide Canadian farmers with valuable research data and tools to help make decisions on their farms. PAMI works in grain storage, harvest losses, energy involved, and energy efficiency, and water management are just some of the areas that Charley's been involved in the last 6 years. She received her bachelor's and master's degree in biological engineering. That's a hard program. From the University of Saskatchewan, and her time off helps raise cattle on the family farm just north of town here at Rivers. So we've got some great local and international experiences to bring to the question. And I'm just going to let some people sit down and ask the AV people, have we got it in order of who's first? Doesn't? Okay. Yeah, Stephen's first. I thought so. But the way the chairs are, they were a bit different. So I'm just going to wait 1 second there, Stephen, and then I'm going to hand you a microphone. Okay, you might as well come on up now. Yeah, folks have taken their seats.
Well, so thanks very much for inviting us. Daryl introduced me already, so I'm going to jump in because we have a limited amount of time. So I wanted to put a really complex slide to start, even though Yvonne did a great job defining what soil health is. Soil health is so complex because it's everything that's going on in soil interacting. But like Yvonne said earlier, it's basically those chemical and biological and physical things that are going on in soil that move water through or allow nutrients to be available to plants. So let's first just recognize how complex an issue it is. And for me, when we want to talk about soil health and how to manage soil health, how to understand it, I think we first need to, before we talk about measure this or measure that, we need to talk about what major limitations from a soil perspective do we have. So do you have erosion, wind or water erosion? Do you have salt? Do you have compaction issues or sealing? So, let's first try and address major limitations to your crop production from a soils perspective before we talk about, this indicator or that indicator that you can get on a soil test. And so Daryl asked me to talk about what should we be measuring in soil, and that sort of makes me think about also how we should be measuring soil. And I think first I would say probably if you're paying attention to your soil health, if you're taking soil samples, if you are sending it to a certified commercial laboratory, you've taken a big first step, and that's good. Whether that's part of your fertility planning for nitrogen management, or whether you're tracking your carbon levels, or otherwise, I think you're in a positive direction if you're paying attention and you're tracking. So as in, you can, if you're going to make a management change, whether you're going to start cover cropping or change your rotation or start adding manure or something, take some benchmarks. Benchmarks, we mean like take some samples across the field, make the management change, and come back in 2, 3, 4, 5 years and do the same measurements again, use the same lab if you can, make sure it's the same method if you can, so your soil health apples are being compared to soil health apples, if you follow me. So I think that's good, and keep in mind variability across your landscape, whether that's the slopes or the salts or whatever. So put that into your plan, and the Manitoba Soil Fertility Guide has a section on sampling strategies. It's available on the Manitoba Ag website. So we had, thanks to funding from Poulsen Soybean and corn growers, we had a couple of different trials, and I'm not really going to jump too much into what we found. We had a tillage trial at Portage, and we had a crop rotation trial in Morden, and Yvonne kindly let us sample some of her fields as well. I'm not going to go into really those details there, but a couple of points I wanted to make were that a lot of, if you want to select what soil health measurements you want to take, what we found, at least in that study, those sort of oldies are still goodies, as in your nitrate is still really useful, pH, soil texture, those things that your Olsen P, those things that you, traditional, let's say standard soil test indicators are still really important to your crop productivity, in this case, yield. And what I wanted to highlight there was those indicators relevant for yield are not always the same for protein and oil. That's what we measured in this study, and they won't be the same in the same year. And I'll sort of come back to that at the end of the presentation. So I'm going to pick on something Yvonne talked about, not what you talked about, one of the things you talked about, as a sort of example of the story of a soil health indicator. Just as an example, it happens to be the same one that you discussed. So this, if you weren't here earlier, I'll just give a really quick introduction. This active carbon, or POC, depending on where you get it, permanganate oxidizable carbon. It's about 20 years old or so, and this was the description of what we were told it was doing. It's meant to be that fraction of carbon that would be the canary in the coal mine, that indicator, that first thing that would change if you were to address your total carbon stock, like the first thing that would change in a change in carbon stocks. So really interesting indicator, and as Yvonne showed, and I'll show, can be useful. So there was a study from Missouri, US, so from cornfields, a big number of cornfields at 450 sites. They found that active carbon was a useful thing to measure in soil, so an indicator of soil health in terms of corn grain productivity. But I wanted to highlight that number, that 415 ppm epoxy or active carbon. They said, well, in Missouri, in these large number of fields, this was the threshold, as in, like, here's where you wanted to get to, and it didn't matter afterwards. 415. So these are our data from Manitoba. Our median, so the middle of our data, is about 800 ppm. So more or less double the number that in Missouri they said is where you need to be. But most of our fields in Manitoba are way above that. So what I'm trying to say there is when you're getting information from other places around the world, and they've demonstrated that something is useful, just be careful how you interpret it when you come to Manitoba. High organic matter soils, high pH, things can be different. So just really quickly, in our study, these are data from Portage. Those lines are like this. So it just means that the crop yield, and this is well, we did it for 3 years, but this is just 1 year. Canola, corn, and soybeans, that active carbon number had no relationship with yield in those years. And then we come to this sort of end of that story of one indicator. So 20 years old, this indicator, and then we sort of are reviewing, well, what really does this chemical method mean? What is it actually measuring? And so this is a study that found, well, actually, it's lignin, so a really recalcitrant, so like a slowly decomposable organic compound was responsive to the method, as in, so that's not something that we were told should happen. So it may be that what the method is measuring is not what we were told it was measured. So that's all really just to say we can see utility in the method. Yvonne showed that earlier, but we just need, when you see, oh, there's this new hot thing, I want to pay for that because I've been told it might be useful, just to be a little bit cautious with what you're selecting when you're doing your soil testing. That's really what I wanted to say. So that's the not that Daryl said. And I wanted to comment just really quickly, lastly, on soil health indices. So these are, if you've gotten a soil health test and you get a value and then you get an index number and you think, well, what does that mean? Well, it's sort of, they've looked at all the things that you measured and they give a value to it, a number, say from 1 to 10 or 1 to 100. And then they look, then they sort of sum all of those up and they say, well, this is your overall score. So your field is a 75 out of 100. And well, what does that mean? And how does that relate to yield? So these data are from cornfields. Again, this is in North Carolina. The point is that your growing conditions, your temperature and rainfall in any 1 year will overwhelm your soil health score. So if you think about carbon changes really slowly in soil. 5 to 10 years, you might get a shift in your organic matter. So your soil health score, based on that, might not change a lot from year to year, but your corn yield will based on your moisture. So again, when you're trying to interpret those numbers you get from your soil health test, keep that in mind. That's all I wanted to say. Just to acknowledge the funding agencies and new and old technicians around. Thank you.
All right, so I'm a microbiologist, and Daryl invited me to talk about beneficial microbes in soil and how they connect to plant health. And I debated about a couple of different messages that I could give in these short prepared remarks, and in the end I've decided maybe I should just lay out nitrogen fixation clearly, make sure everybody has a good understanding of that. So that's what I've decided, and if you wanted to hear other things or you want to talk about microbiomes or whatever, you can ask me about that in the discussion section. So my prepared remarks are just going to help you get a clear understanding and an accurate understanding of nitrogen fixation relevant to pulses and soybeans, obviously. So everybody who's in farming knows that nitrogen is hugely important to plants. Perhaps you know, maybe you don't know, most of the air around us, most of the air that we breathe is made up of nitrogen. The problem is that it's in a chemical form that we can't access, and plants have the same problem. They also are taking nitrogen in and out of their leaves perpetually and are unable to use it. So that's what the little pie chart is showing. All the blue area in that pie chart represents the fraction of the air around us that's made up of nitrogen. So the trick is, how do we convert that chemical into a different chemical that plants can access? This is how nitrogen fertilizers are made. You see the big industrial plant featured there that's taking nitrogen literally out of the air and making fertilizer out of it. It's accomplishing that through an industrial process that relies on very high temperatures and pressures and chemical catalysts. So we're talking, we need 500 degrees Celsius, we need 100 atmospheres of pressure to make this chemical change happen, to build this, or to convert this nitrogen into fertilizer. Legumes, pulses have acquired the ability to do this over evolutionary time at room temperature with 1 atmosphere of pressure, substituting instead biological processes, enzymes and cellular energy to do the same conversion. They're making the same form of nitrogen as our fertilizer is, but they're doing it without the industrial process. So this is really central to the climate friendliness of pulse crops, is that we let the biological processes do these things that otherwise we have to spend tons of energy to produce our fertilizer at, with the high temperatures and pressures. Instead, the plants are doing it in the field without that industrial input. It's a big part of why pulses are an important part of the climate-friendly agriculture that our governments and our society want us to develop over time. Okay. Not actually the plant that does that, though. The trick that the plant has acquired is the ability to invite in and to make a home for bacteria that do that. That's a very delicate conversation that happens. Plants are used to defending themselves against pathogens, like we heard about from Shaima's talk. They have all kinds of defensive strategies and barriers and so on. And so for this close, friendly interaction to develop is a very intimate and precise chemical dialogue that happens. The reason that's relevant is that it means from one pulse crop to the next, they're not going to be able to engage with the same bacterial partner that does this nitrogen fixation process. So if you have soybeans on your field and a couple of years later you come with lentils or with dry beans or something, yes, they might both be fixing nitrogen, but it's going to be a different bacterium associating with those crops. Okay, so that's relevant in terms of you're thinking about, are the bacteria there that I need my crop to recruit and to work with to do this nitrogen fixing process? All right, so trying to boil this down to simple points, like what you need for nitrogen fixation to happen is you need the right kind of bacteria and you need it to be alive when the right kind of crop encounters it in the soil. So the kinds of scenarios where this might become relevant are things like thinking through your rotations. It's been 5 years since I had lentils in this field. Are the bacteria that my lentils need to fix nitrogen still going to be there or not? Maybe soybeans still expanding. Maybe you've got a field that's never encountered soybeans before. Is the bacterium that the soybean needs to engage with to fix nitrogen going to be there if there's never been any history of soybean in that field, right? You're going to have to bring the bacterium along with the new crop. Or if you've had some extreme weather events, if you've had flooding or something, you might begin to think about what's happened to these beneficial bacteria that I need to be persisting and present in my field during that adverse experience of the flood. All right, I think every farmer knows that fertilizer is expensive. You probably know it better than anybody how expensive it is. This biological process, while it seems to us sort of easy and free and incredibly cheap, it's still expensive to the organisms that do it. So the bacteria that are making that conversion of nitrogen are spending a ton of energy to do that. And so there's an incentive for them not to do that any more than they need to, or maybe to cheat a little bit and find a nice home inside the plant, but then not do their job and just benefit from all the supplies that the plant provides them. So there's a problem we can have where our plants can become nodulated by these kind of wild rhizobia or these inefficient rhizobia that might even produce nodules but aren't necessarily fixing a lot of nitrogen. And so that's part of the motivation for inoculants, is that you want to have your plants nodulated by strains that are working hard at this process that we're trying to get, and not these wild strains that may not be doing it particularly efficiently or to a high degree. It's also expensive to the plant. The plant does have to feed all of these bacteria inside the nodules of their roots. And so the plant is going to minimize that investment as well if it can. So you do need, you need to supply the plant, or the plant needs a supply of nitrogen in the soil until the nodules kind of develop and begin fixing their own nitrogen. But if there's too much nitrogen available early on, the plant may, anthropomorphizing, but the plant may think, you know what, I'm soaking in nitrogen here. I'm not going to pay these bacteria to make more nitrogen. So if there's too much nitrogen early in the season, you might have a plant reducing the amount of nodules that it forms because it thinks there's plenty of nitrogen. But then later in the season, it may actually become deficient because it hasn't adequately housed enough of these bacteria to do the nitrogen fixation. Okay. All right, so some of that lead up is just to say, very often, most of the time, if you're planting pulses or soybeans, you may want to be inoculating the bacteria along with the plant. And so my first point is just to realize that that is a living thing. So you've got your jug of inoculum. That's alive. Like, you can't see the living thing in there, but there are tens of billions of live bacterial cells in there. And if they die, they're not going to accomplish the thing that you're trying to do. So proper storage, handling, and timing of inoculum is really critical. It might seem like kind of fussy, or the label might say, apply this to your seeds and plant them within 8 hours or something like that. Seems crazily short. But it's because you're dealing with a living organism and you need to get it sort of back into a friendly environment before it dies, and then you've kind of wasted your money there. The same thing with expiration dates or other stresses. If that jug of inoculum gets really hot, you might have just killed all of those bacteria that you had there. And they need to survive in the soil long enough for the plant to produce roots and for this interaction to happen with the roots. So for example, if you're planting into very dry soil, then sometimes it seems that going with a dry, like a granular or a peat-based inoculum might work better than a liquid inoculum. And that seems to be because the bacteria in the liquid are a little bit sort of primed for activity. If you put them directly into very dry soil, they might try to grow and sort of find an unfavorable environment and die. Whereas granular products, they're a little bit more protected. They're going to wait to become activated until they get wet, at which point the plant also will start its activity. So just think about the inoculum as being alive. Be aware of that what you're farming with these pulses and legumes is also a crop of bacteria, and they are the ones that are doing this beneficial nitrogen fixation process. The pulses and the legumes are great for nitrogen, but all that they're getting from those nodules is nitrogen. And of course, they need, you need to manage lots of other things as well. Microbiology connects to many of those things too. There's microbial influences on phosphorus availability. There are mycorrhizal fungi, which are a whole different kind of interaction. Microbes are important for processing and decomposing, your crop debris. There's a lot of connections to plant disease, beneficial microorganisms that reduce the success of pathogens and things like that. I don't have prepared remarks, but I could do Q&A with you on that. So that's what I wanted to talk about.
Perfect. Well, everybody so far today has talked a lot about soil health, and I'm going to kind of take a bit of a pivot in a different perspective. At PAMI, we focus a lot on machine interaction with our ag environment, whether that be the soil or the crops that we're working with. And so Daryl asked me to talk a bit on that, and we've done a couple, starting to try and get into some research projects looking at the effect of compaction. But I want to start with kind of your two main soil machinery interactions throughout the year are tillage, and this is well documented benefits of conservation tillage, kind of reducing erosion, increasing water infiltration, soil water storage. and improve soil organic matter. So lots of that's out there. That's not a new story. And then the other piece that it happens all the time is just that machine traffic on the field, and this is how it impacts the soil compaction. And so this is a piece that I'm going to talk a bit more on, but really that compaction leads to poor water infiltration, poor aeration, and can inhibit root growth and reduce yields. So we talk, word we kind of are using more is trafficability. So this is defined as a soil's capability to support agricultural traffic without degrading soils and ecosystems. And in particular, it refers largely to soil moisture conditions, providing or restricting field traffic by machinery. So really thinking about if your soils are healthy and in a good condition to be able to allow you to traffic on those fields and do the operations that you need to put the crop in the ground and take care of it and harvest it. So, but the big thing is equipment's getting a lot larger, both in size and in weight. So this keeps increasing the risk of soil compaction. And so this is something we want to look more into. A lot of work had been done, but as those machines continue to get larger, what impact does that have? So if we look at kind of the shallow soil compaction, so that's in that top 6 to 10 inches, so that has a lot of impact on your year, within year growth. So thinking about emergence, plant growth, and root development, so I'll show a couple slides. But if we break it down, that shallow aspect is really impacted by the ground pressure of your equipment, whether it be your tires or your tracks, and you want to try and minimize that ground pressure. And the formula for that is just force over area. So if you think of force as being the weight spread over the area, so the larger footprint you have, the more spread out the pressure is, and the less ground pressure. So if we're looking at tires, higher inflation tires will cause greater ground pressure. And so if we start looking at duals or wider tires, that spreads out the area component. And then if we look at radial tires in particular, have a larger footprint than bias ply tires, so same story. And then lots of different options in tire studies coming out to try and improve or reduce that ground pressure to be able to both, but still be able to support the weight of the equipment. Most important, make sure you're using the correct load inflation tables for the axle load and tire size. So a lot of things, when you bring them home, tires are inflated to what you need to be able to, for road speeds, and to be able to move it between. But that might not be the same for when you get in the field. You want to reduce that. So you're using the minimum inflation you can. Of course, it depends on the type of tire. And then tracks also have a larger footprint and are getting really common, especially in certain soil types. But they can be comparable to low ground pressure tire options depending on the configuration. So they're not necessarily better, but they are an option that spreads that weight out for that shallow soil compaction effects. So this is just an example, kind of you can visibly see, and then when we bring in that moisture element, so on the left, you might see a little bit more rutting in the field compared to on the right, and so the left side had that higher moisture. So just a visible observation on that one. And then if we look at deep soil compaction, so this is where you start impacting your water infiltration and your year-over-year soil health. And so the deep compaction is a lot more impacted by the overall force applied to soil. So this is your axle load. So when we talk about that ground pressure, it's spread out evenly, but still the actual total force being applied to the entire system as equipment gets larger increases. And And really, we keep getting larger equipment to cover more acres in less time, and that also means need to carry more product, regardless of the operation. And if we just look at even just the air cart, this average size is increased more than doubled over the last number of years. And even though tire sizes have also increased to be able to hold that equipment and keep it from sinking to the soil is really the ultimate manufacturer's goal. We've changed that. We've kept that soil surface pressure probably similar in some cases, but like I said, the entire stress at lower depths is still impacted. It's just something to keep in mind. These are just examples of a one site year project that we started looking at tires and tracks with different axle loads. And all I want to show from this is that this is using a penetrometer to look at the compaction at different depths. And so you can see that it's not consistent compaction throughout the entire spot. So I don't want to take any saying tracks are better or whatnot, because this is just one single site, so haven't dug deeper, but just think about the depth of the compaction and how that might be affected. So hoping to do more work to expand on that. So other just consequences that I talked about. So this is an example of reduced plant emergence along some track lines. So that kind of starts off your plants on the wrong foot. And then if we look at yield, so this is the project I was talking about. And so we took a controlled traffic field, so known compaction for a fairly long history. And so the lines, here, going that way are the actual tram lines. And then we drove a grain cart perpendicular to those at various loads to look at the compaction effects and effects on yield. And even if, before we go into yield, you can visibly see them. That's just from one single pass, right post-seeding, and how that impacts. And so there were inconsistent yield effects depending on tires or tracks and axle loads in this particular year. But even if just we look at, we can't deny that there's some impact, and that's just in the single year. And so just lastly on that, if we think about like how do we manage our compaction, so we'll say a lot about that like natural freeze-thaw cycle here does help to reduce that year over year between year compaction in that shallow layer as those water and pores freeze and expand, causing more fractures. But it probably doesn't resolve all deep compaction, and you start to get year over year impacts likely. And then you start thinking if you get really compacted areas, having to do some deep tillage to break up, that's counterproductive to our tillage practices, as well as being a pretty intensive operation. So we can start thinking about things like maybe controlled traffic farming in some capacity, maybe not to the full extent of fully dedicated tram lines, but trying to limit the amount of space so you have compaction on a more specific area rather than all over the field. And also, this comes back to various aspects of your farm operation, but choosing appropriately sized equipment. Think about both from your whole farm logistics, but the production costs and the impact on yield. So we're hoping to do a few more years of study on this project specific to the larger equipment. So hopefully that'll be coming out soon. And that's it.
Thanks, Charley. Okay, so we've got three experts from sort of different areas of research. We've got a soil ecologist, microbiologist, a soil scientist, and an engineer. What we're exploring here today is how those are all connected in terms of their impact on soil health and crop productivity. So any questions for any of these folks on things they've said or things you might think they would have in common? Any questions I'm going to take this mic off. Oh, maybe I won't. There we go. Okay. Any questions? I can kick. Right. Is there a question there? Yes. Go ahead.
There's just a tremendous number of biological products in the market currently, and many more coming, I'm sure. One statement that I heard recently was that a lot of these products are really not that effective on a soil with a low soil health index. Just due to very low survivability of those.
So I think Steve maybe, so biological products, and are they really, do they have a lasting ability to make an effect on soil health? Did I get that right? Yeah.
Particularly in a soil with low soil health
Okay.
index.
Yeah.
I mean, one of the things with biological products, and you mentioned it there's an ever-increasing number of them, and so it's, from a scientific standpoint, it's really hard to have that backing of reliability and effectiveness. And so I guess, if you want to know about investing in something specific, I guess do your homework first before you do that. But about the relation with the soil health, a low soil health score, like I said those major limitations, whether soil or growing conditions, are really going to condition to a large extent what the yield is and the productivity is, or anything else, any other service that's coming from the ecosystem. So I don't know that you would necessarily link those two things, if you follow me. If you wanted to hone in on something more specific, like for example, this product would be related to this one part of soil health, one indicator, one process happening, then maybe it would be true. But specifically I can't say. Do you want to comment on?
So that is that's a tough issue to face. Like I'm kind of interested in inoculants and microbial products. I think there's potential there. Whether they're like actually going to pay off yet, I'm not sure. But in terms of like future technologies, I think there's a lot to be gained from better harnessing the functions of microbes. But I would say you want to have some particular function that you're looking for, and you want your inoculant. You have to expect that it's going to do it better than the microbes that are already in your soil. Like there's already thousands of different kinds of microbes in your soil. Why should you expect this one from the outside to do it better? You have to know, what is the function you're looking for, and have a reason to expect an improvement, I guess. Like I just talked about with the nodulating bacteria, we know that some of the inoculants are better than the native strains, so there we have good support. But whether we can get other functions that also pay off from inoculants is, I think, we're still in early days there.
So the soil is an active, competitive environment. What you're saying is just because you add something doesn't mean that it can overcome all those other things and go in and do its job. The rhizobium and bradyrhizobium that act as inoculants for soybeans and pulses, they form a special relationship with the root. They've kind of got a destination to go to, so they can stick out amongst the overall soil life, where some of these things that you might be told to add into your soil kind of have to compete.
That's right. I mean, basically the nodule is, the plant has just built a home for a certain kind of bacteria, so that bacterium benefits from, competition-free environment and protection and all of that. Whereas lots of other inoculants that are not going towards that kind of a tight relationship with the plant, it's a lot less clear how they establish or how they persist in the face of all the competition from other existing microbes.
I'm just going to say, we're getting a lot of questions on that. Do these biologicals work? And we are doing research both at the laboratory level, but also on farm. And here, Chris, he's at the top by the table there. He's our on-farm network agronomist. And Laura and Jen Jen's up by Chris and Laura's up by the rails. If you wanted to speak to anyone interested in the biological products and their performance, with respect to pulses and soybeans. If you want to talk to them about a test, we can certainly consider that. Up at the top there, sir.
Synthetic nitrogen, is there a safe rate to apply that does not negatively affect my microbiome?
Great question.
Is there a safe rate of synthetic nitrogen to apply that won't affect the microbiome? So I don't know that I can answer that as directly as you'd like, but there's going to be like a gradient of exposure, right? You don't apply your nitrogen uniformly across the entire soil volume. So if you're, banding it in or something, I think you are getting effects immediately in the band or right where you're applying those high doses. But just a short distance away, the effect will be negligible. So it's not a yes or no, it's in precise locations, you are probably killing some things with that nitrogen application. The recovery, I think, would be quite rapid as well.
Great. Okay, I wanted to get a, sorry, was there another? Yes, right next to him. Yeah, go ahead.
Is there any test that you can do to see if you have enough mycorrhizal fungi to not put phosphorus on?
Can you test for mycorrhizal?
I know how we test for mycorrhizal colonization in a research setting. I don't know whether there are commercial tests available or anything like that.
But it does sound like if we could develop something that could guide your phosphorus application, that might be an economically attractive proposition right there. I wanted to ask Charley, we saw the difference in compaction through the profile. And Shama, I think, had to leave. But what we heard earlier on, that it's water in the soil that is causing these oospores, these Aphanomyces diseases, to thrive and to germinate and to infect our crops. So my question, and I don't expect that you've researched this, but maybe just take a professional thought through it. Are we creating pools of water in the profile due to compaction that might be homes for these oospores to live? And because we're seeing we're seeing root rot developing even when it's not really a wet year, but it's developing here and there in the soil, but not everywhere and not all the time, even in what we might consider a dry year, which is why a lot of people grow peas if it's a little drier. But do you think that compaction might be creating pools of moisture in the soil profile? Is that possible?
That's a good question. It'd be worth looking into. Kind of, if we think about, we could like similar to how you can see crusting on the top. That's not to say that those compaction layers slightly deeper in the ground are causing kind of changing how the water sits. And maybe Stephen has a kind of thought on.
I don't know if I have a better answer than that, but what you pose is logical. I guess what we might say is keep in mind that what you might be doing at the surface might have below ground impacts, and that those things are all sort of connected.
Thank you, by the way, for saying I'm logical. I wish my wife were here. Anyway, any other questions? Oh, I got one up at there, yeah, and then next on to you. So go ahead, sir.
So the question is about the question is about whether there's a legacy, like a leftover influence from using different end products on. Is that a good one for you? Yeah, okay.
So I think the question is about nitrogen stabilizers in anhydrous ammonia and if they might negatively affect rhizobia in subsequent years. That's a tough question. I'm not aware of specific information about that. So you could reach out to me and I could look up some info, but I don't have it handy.
I'm just going to butt in there and say, you know what? That's why it's important that we have local research. I'm going to say there probably hasn't been a look at that question, But it's something we need to look at, and we need to look at, here by Ag Canada, universities, looking at those kind of questions in our system. So good idea. And there was a question here. Thank you.
On the compaction, if you have a nice square section and you're farming a north cellar, would there be any reason to switch and farm it east west like every 5 years?
I can't think really. I think the benefit, yeah, if you can keep going the same way, and if, like you said, nice square field, that it makes sense, that, and if all your kind of equipment is well aligned, that you can kind of keep to those dedicated tram paths. I know there's lots of guys that do that, so there'd definitely be somebody to ask somebody that does do that practice, whether they've seen any impacts, legacy in that 10-year range, but offhand, I can't think of reasons.
I think I'd like to know if you've done that and why you might do it, but I think the thinking with the controlled traffic farming is to minimize the surface area that you're compacting. And so, I mean, without having done the research, I would worry that you might, because compaction's slow to recuperate from. So if you are compacting in this direction for 5 years and then you go that way, I wonder if you might end up with more area compacted. But just a thinking.
Lots of questions. Stephen, you mentioned that in your experiments, soil, or someone else's experiments, soil health index wasn't related to yield. Like, it was hard to nail that down in a given year.
Yeah.
But we know that soil health is something that evolves over years. Would you bet that it may not be related in a given year or in year 1, but by year 10, if someone's been working on their soil health, that you would see a relationship? Do you think that's something that would?
I like that question, Daryl, because you provided part of the answer already in the question, so that's great. Thank you for that.
I'm logical.
No, I think I was trying to caution people by to not get too hung up on a number in 1 year kind of thing. And it's, like I said, it's great that we're soil testing, great that we're paying attention to soil health, because it can relate to your crop productivity, your carbon storage, your water movement. So there's it's a win-win, as you say. So there's a lot of reasons to pay attention to it. The hope on the carbon side is that carbon tends to change pretty slowly with time. So the hope is that from 1 year to the next, to a dry year to a wet year, that greater soil health would give you more stability with time. So I think I'd be more interested in that yield, that 10-year yield stability number, than this year or next year.
So stability. Okay.
I mean, that's, yeah.
Yeah, and this is what healthy soil, it sort of boosts productivity. What it does really is stabilize and give you some risk management. We got about 4 minutes, and we're going to key up that video, right? If I got that right, in about 4 minutes. Okay, one question here. Yes, sir. Micronutrients and nodulation. How's that one?
Okay, well, the one connection that comes to mind is that the enzyme that does this conversion of nitrogen requires a cofactor element, which, all of a sudden I'm not sure, but I think it's molybdenum or something fairly weird. And sometimes the amount of nitrogen you fix can actually be limited by how much of the cofactor is available. So in certain soils, I don't think it's true in Manitoba, but in certain soils, you can get a nitrogen fixation boost by applying molybdenum, because it helps the enzyme that does the transformation. So that's a specific instance. More generally, I'm not sure how frequently we are micronutrient deficient in these soils, but there could be an effect mediated just through sort of general. If the plant's limited by something else, it might restrict resources given to the nodules, sort of to try to balance out its competing needs or something.
Oh, yes, one right here.
That's a good question, and I don't have the answer for it off the top of my head.
I think depending on the soil texture, type, drainage, moisture content, I've seen data for up to 3 feet. But so I guess depending on the soil condition, compaction can be pretty deep, depending.
Thank you for mentioning the salinity word. We haven't talked about salinity today, and we purposely kept it off the agenda because it's such a big and complex thing, but it is important, and I think you will all agree that salinity has started to creep its ugly head again in various parts of Manitoba. Compaction has a lot to do with it. Water management has a lot to do with it. And we're concerned because our crops, soybeans and pulses, are particularly sensitive to soil salinity. And we are investing in research to improve the tolerance of particularly soybeans to drought and related stresses like salinity, because it's such an important thing. Folks, I just wanted to thank the panel we had here today. Very stimulating, very interesting.